Okay, so today we're going to talk about areas and length of polar curves. So we've learned about sketching, understanding curves where the radius is given as a function of theta, right? So we did I can't remember the exact example we did, but we did a specific example of this, which turned out to just be a circle, right? And what we're now going to learn about is how to actually find the area swept out by a polar curve. So if, for example, we are interested in the area swept out as we go from angles, say A up to angle B, right? So for every angle between A and B, r of theta is some particular defined function, right? So this might be what we're sketching out, something like this. No? Then this thing has obviously an area. We just see it, right? This is the area we have. And we want to know what the area actually is. We want to be able to explicitly calculate it. Yeah? And to do this, obviously, we need to have some kind of a formula, right? And that's the first thing we have to figure out. Once we figure out what the formula actually is, then we'll be in a position to just do this calculation and practice it. And that's part of our task of today. So first, let's figure out what the formula actually is. So let's think about some very special cases. Suppose we just have a constant function, right? So if r of theta is just some constant thing, it's just radius r0, yeah? Then if we say, look at this area swept out between 0 and some particular angle, let's say it's angle theta, yeah? Well, if the function is just constant, then we're just producing a circle of radius r0. It's not necessarily a bad circle, but you know what I'm trying to do, yeah? So the area we are thinking about is this area. Can we figure out what this area is? Do we have a way to do that? What do you think? Just using elementary stuff that we know already. So think about what's the total area of the circle, inside the circle, yeah? And think about what proportion is actually inside this little slice that I've drawn. Yeah, we could try that, and we might succeed because this is a graph up to here, and this is a different graph, yeah? But that would be quite hard work. So we're going to try and do this with as minimal work as possible. So here's a way to think about it. So the total area of inside the circle, right, is what? It's just r0 squared times pi, right? Because we know the area inside a circle. And then we ask ourselves, what proportion is inside this slice part here, right? What proportion? Yeah. Well, the angle goes from 0 up to 2 pi, right? So if we were interested in the entire circle, then it would just be everything from 0 to 2 pi. If we're interested in just half, it'd be everything up to pi, right? Yeah. So if we think about it, the amount of area inside this pi slice of the actual circle will be given by the total area times whatever percentage is inside this thing, yeah? Whatever fraction of the total area is inside this thing. Whatever fraction will be the angle divided by all the possible angles. Yeah? So this thing is the amount, the percentage of the entire interior of the circle inside this thing. Yeah? And this is the total area. Let me just check it, right? So if for example, theta is equal to pi, then that's clearly half the circle, and then this quantity is half, yeah? If theta is equal to 2 pi, that's the entire circle, and this is equal to 1. If theta is equal to pi over 4, that's clearly a quarter, and that's a quarter, Yeah? So this thing is indeed giving us the proportion of the circle inside this slice. Yeah? Give me a thumbs up if that makes sense to you. Cool. So this thing should indeed be the area in this, and it actually is, right? So theta R0 squared over 2 is the area inside here. So we can do this in the very special case that when we have a constant function. A constant function, right? Okay, but the thing that we are exploiting all the time when we're figuring out explicit formulas for things is that on a very small scale, things look very simple by differentiability, look kind of like this. And then we have the ability to put things together with this generalized form of addition called integration. And that is what I call the Riemann-Sum machine. We've done it lots of times before. We're going to do it again to get the formula, right? It's not a big deal. It's not a difficult thing to do. So if we start from A, we end up at B, we're going to cut this thing up into this thing. So when I first started doing this, I said, if you get comfortable with this, it'll save you a lot of time and mental energy, because it's exactly the same procedure every time we have a formula in calculus. And all the formulas in calculus just fall out in this same very simple way of just cutting things up into small pieces, understanding the small piece because it's very simple in structure, and then adding them up. So this is yet another example. We're going to continue to do this, and you'll do this every time you learn something new in calculus. So if you're not comfortable with this by this point, please just invest some time. Look at many explanations of various formulas I've done doing it exactly the same way. You'll see that it's really not a big deal. It's really kind of a straightforward thing, right? So it maybe seems like a big deal, very complicated thing, if it's not clear to you. Once it is clear to you, it seems rather straightforward. All right, so let's cut it up, just like we've done it here. So we start with the initial angle. Let's call it theta 0 is equal to A. I want a different pen. And we're going to cut up all these things into n different pieces. So we let b minus a over n be this thing. And then we let theta I plus 1 equal theta I plus delta of theta. And then theta of n is equal to the final angle b. Same as we've done lots of times, right? And then we look at one of these particular guys. So suppose we look at this particular guy right here, this particular little slice, right? So say this is angle theta k, and then this here is the angle as we shift forward by just delta. And we look at that on a bigger scale. So I'm going to take this thing here, and we're going to move the picture over here. So blowing up what we see this angle. So making it a bit fatter just to make a better picture, right? This was the angle given by theta k. This particular angle here is just delta of theta, because we're just moving along by delta of theta, right? And then we look at what this is. So this length here is given by r of theta of k, right? So we have a situation which is pretty much like this, because while this isn't exactly just a portion of a circle, it's pretty close to it, because the function isn't doing very much, right? It's not moving around very much as we look at very small scale, yeah? So we can approximate this with this simple case right here. We can pretend we have just a constant function, because if we had a constant function, it would look almost the same, right? And the error between having when we have a constant function whose radius is just given by this and what the actual function is very, very small, negligible compared to the area of this little slice, right? So we forget about it. So we say, okay, well then this area is what we've just figured out from this formula. It's equal to delta of this thing. The radius is this thing squared over 2. Yeah? Does that seem reasonable to people? No? Give me a thumbs up or so. Cool. So that is giving us the area of that particular little piece. And we have n pieces, so we just add them up together, right? So this area is, I should say, approximately equal to, because it's not quite equal to, because there's a tiny area here. So it's approximately equal to. So area is approximately equal to the sum from k is equal to 1 up to n of delta of this of theta of x squared over 2, right? And what is this thing going to tend to as we let n tends towards infinity? What's this thing going to tend to? What is this general expression called? What do we call those things? It's a Riemann sum, yeah. And what does it tend to? It's going to tend to an integral, yeah? So what integral is this going to tend to? Perfect. The integral from a to b of r of theta squared over 2, d theta, right? And that's the explicit formula, which you can explicitly calculate given any r of theta, right? Yeah. And now it's absolutely inequality, because the tiny errors we had just came from this, that we had a function that wasn't quite constant, and we approximated by something that's constant. So we had a little bit of error just right here, right? And those errors just vanish as we take things with smaller and smaller angle. Let me make an adaptation to show the error. So suppose the function was something like this. So it did something like this, yeah? And we approximated it just by the constant function whose radius is given by r of theta k. Then the only error we see is this little tiny piece right here. Yeah? But this little tiny piece compared to the actual slice is negligible. And as we go down to 0, it just vanishes. It just doesn't become an issue. Yeah? So this is now an exact equality. This is again the yin and yang of calculus. We look at something on a very small scale where it's very understandable because of differentiability, and then we add them up with our generalized addition that allows us to add things over an infinite set, an infinite uncountable set. And these things perfectly mesh to allow us to explicitly calculate quantities like this. Yeah? So we have this, any r of theta we can define. Yeah? Cool. Now, we can make a final little check that this thing actually makes sense. So if this is true, then it recovers this particular formula when we have the constant function. Yeah? And indeed it does, because if we just have the constant function r0, yeah, then r0 can just pull out, and we're just going to have just b minus a, which is just this angle here. Sorry, just this angle here. So we get exactly the same thing, right? So in this example, then a is equal to 0, b is equal to theta, right? And then this thing is just r0, so we pull it out. So we pull out the half as well. So we just have r0 squared over 2 times the integral from 0 to theta of 1, which gives us exactly the same thing like this. Yeah? Yeah? Cool. All right, so let's use the formula. Let's actually calculate some things. So this is example 1. Find the area of one enclosed loop of the 4-leaf rows. So I'll explain why they say the 4-leaf rows. Given by r of theta, given by cosine of 2 theta. All right, so on the last class I said this is an example which I've done in a previous class. The video is online. It's actually in this section called short examples or short videos. At one point, I thought it'd be a good idea to make shorter videos and put them in a playlist. I didn't get very far, but I certainly did do this one. And this is not a trivial thing to sketch at all. So please watch this video because it's a kind of canonical example of sketching a polar curve. We have to do the same stuff of carefully looking where the radius is positive and negative and reflecting through the origin. So as I did on the video, and as I hope you're going to check out, what we do, we have to plot the cosine 2 theta, which is wrapping, or which is going up and down twice as many times over the period 0 to 2 pi, right? Because we have the 2 theta here. So what's it doing? It's doing something like this, up and down once, and then it's doing something like this, up and down twice, right? So there's lots of up and down, and then we have to break it up into these little intervals where it's positive and negative, and then carefully sketch it. But if we do carefully sketch it, what we find is something like this. It goes like this, goes like this. So I'm not doing it in the order which these petals or these leaves occur. I'm just doing it to get the picture up. This is what the polar graph of this particular function ends up looking like, where this thing here, as you might expect, is angle pi over 4. And this is the angle minus pi over 4. So when it says find the area of one enclosed loop of the 4-leaf rows, it means finding the area of one of these guys. Yeah, and of course, by symmetry, they're all the same. So please look at how I do this. This is a classic, more harder level example. You can do it with exactly the methods that we went over last class, but you have to be more careful. There's more stages to it. It's kind of interesting and fun how this works out as you carefully go over the graph. But once you've done this, then you can ask, what is the area of one of these loops? And now we have exactly the tool to do it, right? We have the exact formula. So all we have to do is set up the integral correctly with the right limits and actually carry out the integration. You know? As in a lot of these things, once you have the right formula, once you believe the formula, then it's just doing some explicit integration. So I'm going to erase the board and then we're going to do... Okay, so once again, area of one loop. Of cosine of 2 theta. And let's put the picture over here. So this is the one loop we're going to choose. So we're going to go from minus pi over 4 to pi over 4. If you're given this question on an exam, you won't be asked to sketch it as well. You'll be given the picture. As a starting point before you actually need to calculate the area. Okay, so this is the thing we have to do. We're going to take this particular loop, so we just have to set up the integral, right? So the integral is going to go from minus pi over 4 to pi over 4, yeah? And then this expression squared of 2 theta squared over 2 d theta, yeah? And that's it. That's it. So we just need to explicitly carry out this integration. You know? And first thing to notice is that this is symmetrical on either side of 0, right? So we don't have to go from minus pi over 4 to pi over 4. We could just integrate from 0 to pi over 4 and then multiply it by 2. Yeah? So if we did that, then we'll have the integral from 0 to pi over 4, and then this thing, cosine of d theta. Cool. And then this thing, we just need to integrate. So we have this identity cosine of phi squared equals 1 plus cosine of 2 phi over 2, this double angle identity. So we're going to put that in. Just going to be integral from 0 to pi over 4. And then we're going to have this 1 plus cosine. Now this is going to be 4 theta, and then over 2 d theta, and then we just do the integration. So then and this will be theta over 2, and then this will be sine of, 4 theta. But if we differentiate this thing, we're going to get an extra 4 that we don't want, so then we are going to divide it by 8, right? Divide it by 8. So when we differentiate this, we're going to cosine of, but we've already pulled out the half, so we don't care about this. Yeah, since we pulled out the half, it's like this. So we pull out the half, so when you antiderivative of this, and do this, then we just need this over 4. And that's it. Yeah? This is our expression. Yeah, we've pulled out the half, and then the antiderivative of 1 is theta, and the antiderivative of this thing is sine of 4 theta over 4. Yeah? And then we just put in the numbers. So as we put in 0 into this, it gets 0. As we put in pi over 4 into this, it's going to be sine of pi, which is 0. So this entire thing is contributing nothing. So it's just going to be this. It's just going to be pi over 8. And that's it. Yeah? Cool. So the answer is that the area in this thing is pi over 8. And the calculation itself is pretty easy. Because, let me do it over here. Thank you for this question. So as we do this thing, so let's just forget about this pi over 2 for the time being. If we had to do this thing, yeah, then this thing is the same as doing this thing. And then this thing, we're just breaking it up, right? So that's like doing the top half and then the bottom half, yeah. But you see that they're the same area because it's a symmetrical expression, yeah. It's the same area, yeah. So this thing is the same as just doing twice the top half. Yeah? So then when we divide by 2, we have that this thing is 1 over 2, this thing. So I did this all in symbols, but in pictures it's just that if we take the area of this entire thing, it's just going to be half of the, it's just going to be, start again. Half of the area of this entire leaf will just be the area of one half of the leaf. So this is the area of 1/2 of the leaf. So that's the area of the whole leaf divided by 2. Is that helping? Thank you for the question. Cool. So that is going from this to this, and that is our answer. All right. Let's do another one. Example 3. So it can get a bit more sophisticated. So example 3. Find the area of the curve inside the circle given by r1 of theta equals 3 sine of theta. Okay, and outside this thing, which is called a cartioid or something. I'm not sure I can pronounce that word correctly. Like this. Okay, so let's first check that we believe this is a circle, because it's also a good example of turning something from a polar equation or polar curve into a Cartesian curve. So if I wanted to try and turn this into a Cartesian curve, tell me what we should do. It's something similar to what we've done before. So we need to turn this into an x and y equation, right? So what are the relationships between the r and whatever in terms of x and y that's going to help us? Yep. Is there any other relations? So we indeed have that x is equal to r cosine of theta just by trigonometry, and y is equal to r sine of theta. Is any other relationships between x, y, theta, and r that are useful? Okay, does anybody remember? Again, it's just falling out from trigonometry. Let's draw a right angle triangle. This is theta, right? This is the radius r. What are the relationships between these characters? So we've named one or two relationships given by this, yeah? What other thing can we say about the triangle where we describe r and theta in terms of x and y? Come on. You probably said the right thing, but I just didn't. I just caught the end of your word. Indeed, it's Pythagoras' theorem, right? Yeah. Cool. With these relationships, then we can try to turn things which are in terms of r and theta into x and y, right? Because then this thing here, this radius, we can think of as being x squared plus y squared square rooted, right? And this thing, 3 times sine of theta. Well, sine of theta is y over r, so that's going to be like y over, or 3y over x squared plus y squared, the 1 over 2. Yeah? Just using this and using this. Is everybody with me? Give me a thumbs up if so. Thumbs up, people, if so. Thumbs down if not. No, this one's going to be this one we're about to see is the circle. This one we're about to see is the circle. So it sort of follows. So it says the circle, this, and outside this thing, which is the cardioid. Okay, so this should turn into a circle. So let's do some cleanup. Let's look at this. We have x squared, y squared equals 3y. Is it looking like a circle to you people? If so, how are we turning this into a circle now? General formula for a circle, right, is x minus a squared plus y minus b squared equals r squared, right? So let's write it like this: x squared plus y squared minus 3y equals 0. Yeah? Not complete the square, right? That might be what the other guy was saying, but let's just complete the square so that we get the r squared in terms of y. So if we do this, then we're going to have this additional 9 over 4. So we're going to have to take that away. And that's the same thing, right? This is the same thing as this thing. And then this is in the form of a circle of radius 3 over 2, centered at 3 over 2. Centered at 0, 3 over 2. Yeah? So then this thing is the circle that looks like this. Here we are. It's centered at 0 for the x and 3 over 2. Right? So a is 0, b is 3 over 2, and its radius is 3 over 2, so it looks like this. Yeah? Cool. So we did an example before where we had a cosine instead of a sine, but it falls out exactly the same way. Huh? Cool. So we believe this is a circle. It's this circle. This shape is harder to draw. It's so-called cardioid, and it's a shape like this one. So let's call this one R1. The other one is some shape like this. It's not meant to be flat at the top the way I did it. It's curving like this. And you can sketch it with the same kind of methods we've done before, but this guy is just longer. We can't quickly get it shaped by turning into an x and y Cartesian equation. So what's the question actually asking us? Find the area inside the circle. So it's asking us for this thing, the area here, inside the circle, but outside the cardioid. This is R2, okay? That's what the question's asking us. This picture might be a bit small. Are you with me? Give me a thumbs up if so, thumbs down if not. All right, so how are we going to start to set this up then? I don't have a watch. Tell me what time it is. We might be running out of time. Okay. Let me make a bigger picture because I think that's making life harder to have my tiny picture. So this is the circle. Okay, and the cardioid is something like this. Okay, and the area we're looking for, I mean, it's meant to be symmetrical across the y-axis. And the area we're looking for is this thing. Okay, this is our task. And what tool do we have? We have the tool to work out the area of inside a polar curve over whatever set of angles we choose, right? Yeah? How can we use that tool to answer this question? Great. Oh, okay. Yes, but okay, so let's find where they intersect. How are we going to use that information? So once we find these points where they intersect, how's that in terms of just practically doing the calculation? How is that useful? What do you mean by from those two? You're almost there. But we integrate over a range of angles, right? We don't integrate from intersection points. So what you mean is we integrate from between them, right? Between the angle that gives the first intersection and the angle that gives the second intersection, which is what you people answering questions were coming towards, probably trying to say, but couldn't express it quite correctly. But that's what we've got to do. Yeah? And we have exactly the tool to do that because, again, we can integrate between any two angles that we choose. Yeah. So once we find the intersection points, we're going to use that to find the angles where they intersect, find the angles where these intersection points occur. And then if we integrate the area swept out by the circle minus the area swept out by the cardioid, that thing will give us exactly the thing we want. Yeah? So setting up this integral because you know what tool you have is the hard thing, and the actual calculation is the straightforward thing. Are you clear about how we're going to do this? Yeah? How we're going to set this up? Is this making sense? Thumbs down if not, because we're about to erase and actually do it. Thumbs up if so. Okay, so this is our picture. Very bad circle. Okay, very crude picture, but we know what we're trying to do, right? So we want to find this angle, and everything is symmetrical, so we should see that when we do the calculation. Once we find these angles, then we are going to integrate the area swept out by the circle, the outer function, minus the area swept out by the cardioid inner function, which I've called R2. In the book, they both call them R. It's a bad idea to do that. So if you are doing this in your homeworks or exam, don't call the same thing. Don't use the same name for two different things. It's the recipe to get confused. Give them different names. All right, so R1 of theta is the circle. It's this guy, 1 plus sine of theta, and the cardioid. Oh, I'm wrong, sorry, that's R2, that's the cardioid. And R1 of theta is the circle, given by this thing, 3 sine of theta. So we start by finding these points right here where they intersect, okay? Where this and this happens. So we obviously just set these things together. So finding where they intersect. Oops. We have that 1 plus sine of theta will have to equal to 3 sine of theta, right? That's exactly finding what angles are such that they intersect. Yeah? That's in the language of math, that's exactly expressing, again, where these things intersect in terms of the angle. And then if we solve this, what we have that 1 will equal to, or 1 over 2 will equal to sine of theta. And then this is solved by theta equals pi over 6, 5 pi over 6. Yeah? So let's check that was what we have. Yeah, that makes sense. So this looks a lot more flat than I've done it. So So this is quite a flat angle. So far from the actual picture, I have to erase it. So this would be like pi over 6, and this will be 5 pi over 6, and they are intersecting like this. Okay. And sure enough, this is symmetrical because this angle here is pi over 6, right? And this thing is going clockwise from pi by pi over 6, right? So from here to here is again pi over 6. It's a better way to express it because this is 5 pi over 6, and then this is pi. So we go that pi over 6 that way to get to this flat line, yeah? So it's a symmetrical point that we've identified, yeah? Which gives us the reassurance that we are doing this calculation right. Oops, and I wrote this wrong. This is 5 pi over 6. Okay, no, I wrote it right, but let me specify. So this is the angle 5 pi over 6, and this width is pi over 6. Okay, cool. So those are the angles where they intersect. Now we have to set up the integral. So we are going to integrate from pi over 6 to 5 pi over 6. And then it's going to be, now this is the point we have to not get things wrong. We have to do the outer function minus the inner function, right? So if we do this like very, very carefully, we would write the outer function, which is the circle, r1 of theta squared over 2 d theta minus this thing, 5 pi over 6, pi over 6. Then the inner function, which is R2, the cartioid over 2, like this. That's what we would do, right? Because this quantity here is everything I'm going to do in red here, right? That's what this quantity is here. Because it's everything swept out between the angles pi over 6 and 5 pi over 6. And then this quantity here is everything swept out here by the cartioid. Maybe those colors look too similar for you. Yeah? So if we take that area and then subtract that area, we get exactly the stuff that we want, which is this area. Yeah? With me? Thumbs up if you're with me. Thumbs down if not. Speak up if anything's unclear. Because that's the general formula that we figured out, right? So thank you for this question. So we learned that this thing is the area swept out by the polar curve between angles A and B. This is how we started. Yeah? Oops. This is this area. Easy to get mixed up. So much new stuff is coming. But that's our general formula. Cool. So we can incorporate this into one line because it's integral over the same thing, right? Over the same interval. So this is 1 over 2 pi over 6 to 5 pi over 6. And then let's actually put in what R1 is. So R1 is this thing. So it's going to be 9 sine squared of theta minus R2, which is this thing, which is 1 plus sine of theta squared d theta. Yeah? So this is our explicit integral that we have to carry out. Yeah? Cool. All right. Now, we can also make things a little bit simpler in that we notice that everything is symmetrical across the y-axis, which is given by pi over 2. Yeah? So we could instead just integrate from pi over 6 to pi over 2 and then multiply it by 2. We could do that. Yeah? And let's do that. So if we integrated from pi over 6 to pi over 2 and multiplied by 2, that would kill out the half, right? So then that would give us pi over 6 to pi over 2. I prefer to have pi over 2 rather than 5 pi over 6 because I don't want to think about difficult angles that I stick into trigonometric functions. And pi over 2, I at least know more easily what it is. And then let's expand out this thing a little bit. So we have 9 sine of this thing squared. And let's multiply this thing out, minus 1, minus 2 sine of theta minus, oops, no. We'll put the plus and do the minus signs later. Sine of theta squared. Yeah? Just expanding this and integrating with respect to d theta. Cool. Now clean it up a little bit. Integral from pi over 6 to pi over 2. And we are going to lose one of the sine squareds like this. And we are going to have a minus 2 sine of theta. And then we're going to have just a minus 1 like this. D theta, right? So this is looking good, except that we have the sine squared, and sine squared is a pain to deal with, but we have this double angle formula, which is 1 minus cosine of 2 theta over 2, like this. Yeah? So that we can turn this sine squared into this thing here. And if we do this, then what happens? Then we have the integral from pi over 2 to pi over 6. And now we're just going to have 4 minus 4 sine, cosine of 2 theta, right, this thing, and then minus 2 sine theta, and minus 1. But if we minus 1, then we have this 4 over here. Okay, let's do it one step at a time. So what is this? Integral pi over 6. Pi over 2. So then we're going to lose 1 here, and then we have minus 4. And then we have minus 2 of sine of theta. And then that's our guy. And now we're in a position to find the antiderivative. And we're going to have 3 theta. We are going to have plus 2 sine of 2 theta. If we differentiate this thing, no, we definitely do want a minus. If we differentiate this thing, we're going to get this thing. Yeah? And then for this thing, we want to have just plus 2 cosine of theta. If we differentiate this thing, we get this thing. That thing should be our expression, and indeed it is. And then if we just put in the numbers, this turns out to be equal to just pi. And that's it. Okay. So let's see what we did. We drew the picture of what we are trying to actually integrate, which is the stuff which is inside the circle but outside the cardioid. Okay. You'll either have something very simple to figure out the polar curve, or you'll have some hint, like you'll have the picture already, or the picture of the harder part already. Okay. And then we said, okay, we draw exactly what we want to find, which is, again, this thing. And our tool is this formula that allows us to find the area swept out by a polar curve over some range of angles, A to B, like this. That's what our tool is. So we have to use our tool for this purpose to say, okay, well, that's the same as finding the area swept out by the circle between this angle and this angle, minus the area swept out by the cardioid between the same two angles, right? That's what the picture tells us, yeah? Yeah? And then we express it. So this is the area swept out by the circle. This is subtracting the area swept out by the cardioid, yeah? And then it's just putting in the explicit expressions and doing a trig integral of the kind you guys have a lot of experience with, you guys can handle, yeah? So setting up the integral is basically the only new, harder thing to do. And knowing this formula, being comfortable with this formula, which is, again, rather simple if you think about it in terms of how did we come up with this by cutting things up in little pieces and thinking about what would happen if we just had a constant radius. And if we had a constant radius, then we just found this formula rather easily because because we considered what was the proportion inside this pie slice compared to the overall area. We took that proportion and then we multiplied it by the total area, right? That's how we got this. Yeah. So when we have the pie slice, which has got angle theta, then the proportion of the pie slice is theta over 2 pi, the total amount of angle. And the total area is pi squared, and that gave us our formula theta squared over 2, right? So not really a surprising formula given these things. Kind of natural, huh? Okay, cool. All right, so practice this. This shouldn't be too hard a topic, and on Friday we'll talk about finding the arc length of polar curves, and I think that'll be it. Oh, final thing. We do, of course, have the next midterm coming up on Monday. The practice exam is out already. You have almost all the content of the practice exam. The arc length of polar curve is the only thing missing. Start to do these things, because I'm gonna hopefully finish up this quickly on Monday, and then we'll start to look at questions on the practice exam. Much better to do them first. And as always, the hint for the harder questions on the exam will be on the practice exam. So know the practice exam inside out if you want to do well on this exam. Yeah? Okay, cool. Thank you for your patience, sticking around. I have office hour now. Stay if you have any final questions. Otherwise, I will see you all on Friday. Bye-bye.